Hi and welcome back. Today I want our discussion to be about one-sided limits. So lesson 4, one-sided limits. Uh, suppose we are approaching, so I'm going to be here on this drawing, suppose we are approaching a point C on the x-axis from the right. A little bit about notation. We're going to denote this as the limit as x approaches C, and it looks like C positive like that with a little plus sign up to the right. But that's read as the limit as x approaches C from the right. And that'll be equal to L. Okay, here, I'll do this in another color, orange. Here, I'm coming in towards a point C, but I'm coming in from the left. So we're going to denote that, the limit as x approaches C, and it looks like C negative, but we read that as the limit as x approaches C from the left. And that's going to be equal to M. Okay? So the right-hand limit as x approaches C and the left-hand limit as x approaches C are given. Okay, this is considered a right-hand limit, limit as x approaches C from the right, and this one is considered a left-hand limit, limit as x approaches C from the left. Okay, that's just to familiarize you with this kind of notation. Okay, let's see what's next. In this next example, and I have written here, it says try putting this function into your calculator for practice. So I'm here at y equals x over the absolute value of x. So we'll go to y equals. It's always good to practice putting functions into your calculator. X divided by, and then I'll hit the math button, slide over to num. Absolute value is that command, absolute value of x. What I like to do is, just to be safe, I like to chunk off that bottom with an extra set of parentheses. Chunk is not a mathematical term, by the way. Okay, so break off the bottom with extra set of parentheses. All right, zoom 6. It's going to be our standard window. Okay, now what's interesting here is if you just rely on the graphing calculator, you have to be careful. So, because it looks as, we're not sure exactly what's going on there, at origin. Now you could do an exploration, so you could come in from the left. Now we've been practicing that. I'm going to go to table set, make sure that's on ask. I'm going to go to table, and what I want to do, let me clear that out. I'm going to delete whatever was in there before. So what I want to do is say, okay, look at the limit as x approaches 0 from the left. So pick a number to the left of 0. All right, negative 0.01. Negative 1. Okay, how about negative 0.001? So getting a little closer to 0, but still to the left. Okay, negative 1. Negative 0.0001. Still looking like negative 1. So it's looking like the limit as x approaches 0 from the left is negative 1. Now, let's look at to the right of 0. Okay, 0.01. Aha, getting positive 1. 0.001. Aha, I'm getting still positive 1. 0.0001. Still getting positive 1. Okay, so let's summarize. So clearly there's different right-hand and left-hand limits at origin here. And again, just to practice using that notation then, we would say the limit as x approaches 0 from the right of this function, which is x over the absolute value of x, we would say that limit is 1. But the limit as x approaches 0 from the left of that very same function, I'm just going to call that f of x here, is equal to negative 1. Okay, so I'm coming in from the left, my functional values are tending towards negative 1. Coming in from the right, my functional values are tending towards 1. And we notice that on the graphing calculator. Okay, so again, that's still practice just using the notation. Let's see the next example. Okay, in this next example, our function is y equals square root of 4 minus x squared. And we see the drawing here. What I'd like you to note is that the left-hand and right-hand limits are equal as x approaches 0. So as I'm coming in from the left, limit and I'll just write it here, limit as x approaches 0 from the left is looking like, and what would that be? 2. Okay. And the limit as x approaches 0 from the right is also equal to 2. If you're wondering how that's happening, just try putting 0 there, and for x, 0 squared is 0. 4 minus 0 is 4, square root of 4 is 2. But you can, you could always graph that on your calculator. You'll see the point 0, 2 exists right here. Okay? So the left-hand and right-hand limits are equal as x approaches 0. And the functional value, I misspelled value there, but the functional value at x equals 0 is equal to the right-hand and left-hand limits. So that will have to do with our definition of continuity. So the function is basically continuous at the point x equals 0. We'll talk about continuity later. But notice the limit as x approaches negative 2, though, only exists from the right, and the limit as x approaches 2 only exists from the left. So what I mean by that is this. I'm going to do that in another color. Maybe red. Let's see. Okay. So as I'm coming in towards negative 2 from the right, I'll write that here. My limit as x approaches negative 2 from the right of my function, that's going to equal 0. But so that's called a right-hand limit. That exists. But there is no left-hand limit because the function itself doesn't exist, to the left of negative 2. Notice the limit as x approaches 2 from the left exists, and that's also 0. So here, as I'm coming in towards 2 from the left, the limit as x approaches 2 from the left is 0. Okay? And that's what we see here with this notation. The limit as x approaches 2 from the left is 0, and the limit as x approaches negative 2 from the right is 0. But they only have, right-hand and left-hand limits respectively. So, we say more formally then, a function f of x has a limit as x approaches c if and only if it has a left-hand and right-hand limit there, and these one-sided limits are equal. So, I'm going to say it like this. The limit as x approaches c from the left is equal to L, and the limit as x approaches c from the right is equal to L. And what does that do? That's if and only if the overall limit exists. And you could say that the other way around. So here I'm going to read it this direction. The overall limit, I like to read this as the overall limit. So the overall limit as x approaches c is equal to L, double if and only if, basically the limit from the left exists and it's equal to L, and the limit from as x approaches c from the right exists and is also equal to L. So basically that left-hand and right-hand limit have to be the same. They have to be equal to L in order for that overall function, overall limit as x approaches c to equal L. Okay, hope that helps. We're going to discuss some more here in a moment. I know what I just said there was a little abstract, so I think this picture will help make it a little bit tangible. Discuss the limits as x is equal to 1, at x equal to 1, 2, 3, and 4, etc. So let's just kind of play with this. What's the limit as x approaches 1 from the left of this function? Well, as I'm coming in towards 1 from the left, what's happening? My functional values are at 0, so that would be 0. All right, what's the limit as x approaches 1 from the right of f of x? Well, as I'm coming in towards 1 from the right, it's approaching 1. Okay, now what's happening then is my left-hand limit and my right-hand limit are not the same. So therefore the overall limit does not exist. So I'll just write that here. In your homework, the author's going to say, what's the limit as x approaches 1, like that, of f of x? The overall limit. And you would say DNE does not exist. Okay? Hope that helps. Let's try another, let's sort of look at another point on the function. Okay, now let's take a look at, let me grab my pen there, let's take a look at the limit as x approaches 2 from the left. Okay, as I'm coming in towards 2 from the left, my functional value is at 1. So the limit that reads as the limit as x approaches 2 from the left, we're thinking that's 1. Now, as I'm coming in towards 2 from the right, limit as x approaches 2 from the right of f of x, what's that equal to? Now I'm coming in towards 2 from the right, aha, still equal to 1. Okay? Well, the limit from the left and the limit from the right are the same. Aha. So then what's the overall limit as x approaches c, where c is equal to 2? Well, that does exist, and it's 1. Now, you may be saying to yourself, and I'm just going to mention this, you might be saying, yeah, but the functional value itself, the functional f of 2, what's f of 2? Well, f of 2 is equal to 2. And you may be thinking, hey, the functional value itself is something different. And that's right. That's going to have, later we're going to ask, is the function continuous at 2? It is not continuous at 2, but we haven't discussed the continuity test yet. That's coming later. It has a removable discontinuity at 2. But at least we know that the limits, the left-hand and right-hand limits are the same, and that the overall limit exists. Okay? I'm going to do one more with you here, just with regard to this picture. Let's just play, let's play with 4. So let's look at the limit as x approaches 4 from the left of this function. So I'm coming in towards 4 from the left, and my functional values are tending towards 1. All right, how about the right-hand limit? Limit as x approaches 4 from the right. Uh-oh. The function, out here in Never Never Land out here, aside of 4, the function doesn't even exist. So d does not exist. So therefore, the overall limit, if there only is a left-handed limit, then the overall limit as x approaches 4 does not exist. Okay? And if you want to look a little further, the functional value itself, function evaluated at 4, appear to be maybe about 0.5. So even in terms of continuity, it's not continuous there either. All right, let's see what we have next. Okay, other functions that are worth mentioning in our discussion on one-sided limits. Oscillating function, it seems like this one keeps creeping up on us, but it's worth taking a look at. Special cases, y equals sine of 1 over x. I'm just going to rewrite that here, sine of 1 over x. So it's oscillating too quickly. So sine of 1 over x has neither a right hand nor a left hand limit as x approaches 0. The graph here, in fact, omits values very, very near the y-axis. So what's basically happening is, as I'm coming in towards 0 from the right, I'm bouncing back and forth right here, so fast that I'm never actually at one point long enough to say that the limit's 1 or the limit's -1. It's oscillating too quickly. So, for example, if I said, what's the limit as x approaches 0 from the right of this particular function, you would say d does not exist. Okay? Okay, in this next example, I wanted to take a look at it. We're not going to prove this theorem 7. The proof is in the text. We're really just going to use it to facilitate some finding of various limits. But let's just take a look at it graphically rather than proving it for now. Y equals sine x over x. So we see, just visually, as I'm coming in towards 0 from the right, so it looks like the limit as x approaches 0 from the right of this function is equal to 1. And the limit as x approaches 0 from the left of this function is also equal to 1. See, I'm coming in from the left, also equal to 1. Even though there's a hole there, You know, at 0, 1, even though there's a hole, the limit still exists. So the overall limit as x approaches 0 is equal to 1. And that's what we're seeing here. Okay, Theorem 7. Like I said, we're not going to prove that, but we're going to use that in these problems that are to follow here. So the limit as theta approaches 0 of sine theta over theta is equal to 1. Note to self, important. I always tell my students in my live classroom that you know, anything in a blue box here in the textbook is probably important. Now let's try some homework together. Okay, now what I did was I cherry-picked some problems from the text that sort of force us to utilize this important theorem. It says here, and I'll rewrite this question, find the limit as x approaches 0 of sine of 2x all over 5x. And then I wrote here, hint, we wish 2x was in the denominator. So that's my first hint. It's like if it was sine 2x over 2x, you would have an idea of what the limit is based on this. So you say to yourself, gee, how could I get 5x to become 2x legally? So now we're going to talk about these algebraic manipulations. So hopefully you thinking to yourself, well, I could multiply by 2/5. Well, that's true. But whatever you do to the bottom then, you got to do to the top, right, to keep it legal. So whatever you do to the bottom of the fraction, you have to do to the top. So what that would do, so note to self, multiply, I'm going to say top and bottom, I mean numerator and denominator, by 2/5. Okay, so that's what we did there. Okay, 5 times 2/5 then is 2, so you'll have your 2x in the denominator, and upstairs you're going to have 2/5 sine 2x. And of course you've got the limit as x approaches 0. Now this, you're noticing, sine 2x over 2x is the same symmetry as sine theta over theta, meaning, you could let theta equal 2x, and we can actually even perform that substitution. Let me do that with you here. So if you go ahead and let theta equal 2x, then by deduction, x would equal theta over 2. So I could store that in here, right? And then 2 times theta over 2 would just be theta. So then I'll just be left with theta in the denominator. And the numerator, sine of 2x, well again, I'm letting theta be called 2. It's like doing a u substitution. You'll have sine of theta in the numerator, okay? And then I'll still have my 2/5 there. And then we'll do limit as, now instead though, we're going to use theta. Limit as theta approaches 0. And now we know that sine theta over theta, we know that the limit of that is 1. So, oops, my pen's getting fussy, so I'm going to scratch that out and put 1. So 2/5 times 1 then is just 2/5. So after all that, we're going to arrive at 2/5. I really just wanted to reiterate here one last time. I hope that helps, but I just wanted to reiterate that once you have created that lovely symmetry of sine theta over theta, so like sine 2x over 2x, whether that's said, sine of gamma over gamma, sine of delta over delta, as long as you have that type of symmetry there, we know that the limit as theta approaches 0 of sine theta over theta is equal to 1. So that's what allows that to go to 1, and then we're just taking, 2/5 times 1 to get 2/5 as our final answer. Okay, hope that helps. Let's try one more that involves a trig substitution, and that'll be our last one for today. Okay, I'm going to read this problem to you first. I took this one from the book. It said find the limit. I have it typed out here, but it basically said find the limit as cos h minus 1 over h. Find the limit as h approaches 0. Okay, but here's the thing. The author tells us, hint, use a half-angle identity to get started. And they give us, cos h equals 1 minus 2 sine squared h over 2. But here's the thing. On a test, you may not have that, so I really do want to walk you through that. Say you're given a list of identities, and we are in the back of our book, but here's the thing. At the back of our book, or maybe you even have memorized the double angle / half angle identities, sine squared theta is equal to 1 minus cos 2 theta over 2. Well, let's manipulate that, okay? Let's cross multiply. All right. Well, then we'll have to, because I want to figure out how, if you're not given that hint, can you do it on your own? Okay. So 2 sine squared theta equals 1 minus cos 2 theta. Okay. Now what I'm going to do is try to get, now here you see in your original you have cos of theta in essence. So you want to try and get cos theta alone. So move 1 to the other side. Now you have 2 sine squared theta minus 1 equals negative cos 2 theta. Okay, well, the negative, clearly we can, negate the other side, right? So if we did that, we'd have then, so, change the sign on the 2 sine theta and the 1, so I'd basically have 1 minus 2 sine squared theta equals cos 2 theta. Now there's something that you're noticing though. Notice what the author gave us was 1 minus 2 sine squared theta over 2 is equal to cos theta. Well, by deduction, think about this. This says that 1 minus sine squared theta is equal to cos 2 theta. So that basically means when one angle is something, the other angle is double it. So you're noticing this is 2 theta when this is theta. So by deduction, when this is theta over 2, this is just theta. Okay? On one side of the scale, it's double the other. So by deduction, that would be the same thing as saying then that 1 minus 2 sine squared theta over 2 is equal to cos of theta. So that's a little bit trippy there. Ran out of room there, but that's basically where that came from. So I hope that helps a little bit in terms of the derivation of that. Now let's just assume that you knew that. Basically that means that you can replace then cos of h or cos of theta with that expression. So let me hit pause and let's do that. Okay, so then I am going to go under the general assumption that you know that cos of theta is equal to 1 minus 2 sine squared theta over 2. We can just take that expression, it's like plug and chug, replace the cos of h with that. Okay, so then we'll have the limit as h approaches 0 of 1 minus 2 sine squared h over 2, okay, minus 1 all over h. Okay, now notice the 1's cancel out. Okay, then you are left with negative 2 sine squared h over 2 all over h. Now something comes to mind. You're looking at this and thinking, oh, I know that, always that in the background in your mind, sine h over h. So the limit of sine h over h, we know that's 1, and we kind of wish we could use that somewhere. So we're going to continue to do like a little substitution here. So let's look at what's inside the parentheses here, h over 2. Let's let theta equal h over 2. Well then, by deduction, 2 theta equals h, right? So then 2 theta equals h. So I can basically replace this h with 2 theta. And I can replace this expression here with a theta. All right? Let me hit pause and we'll do that. Okay, so I just kind of rewrote that a little bit. So we started off with the limit as h approaches 0 of this, which is the limit as h approaches 0 of this after we performed that trig substitution. Then we decided to let theta equal h over 2 so that we would eventually arrive, okay, down here at the limit as h approaches 0. And I should say that now we're actually, that's theta, now we're as theta approaches 0. So we used to be with regard to h, and now we're with regard to theta, because we did that substitution. Okay, so would be, so now the limit as theta approaches 0 then, of negative 2 sine squared theta over 2 theta. And here's where we left off. Now just think about that. We're almost where we need to be. But, you know, you've got sine squared theta over 2 theta, so we're almost there. The 2's cancel out, okay? Sine squared theta really means sine theta times sine theta. So you have sine theta times sine theta over theta. And, of course, the negative 1 out front, okay? Now, right here, sine theta over theta, we know that the limit as theta approaches 0 of that, I'll do that in another color just so we can see it better. You know, the limit as theta approaches 0 of this, we know is 1. Okay? Here, we're left with, in essence, storing 0 in there. So, sine of 0 is 0. So in the very end, we're left with negative 1 times 0, which is 0. So after all that sweat equity, the answer to this one is 0. Okay? A lot of people ask me if they have to perform these trig substitutions and these theta substitutions. Yes, you want to be able to do that. Okay? All right, hope that helps.